Section 3.5, Investigating Graphs of Polynomial Functions. Today you will use the degree and the sign of the lead coefficient with properties of n behavior to analyze, describe, and graph polynomial functions. The graphs of polynomial functions are classified by the degree of the polynomial. Each graph, based on the degree, has a distinctive shape and characteristics. So when we look at the graphs of polynomial functions below, you notice this first one is a linear function. It has the degree of 1. So most of us know a linear function is y equals mx plus b, so you can see that the polynomial, the highest degree, is 1. So the maximum number of x-intercepts equals the degree. So a linear function has 1 x-intercepts. The maximum number of turning points is the degree minus 1. So a linear function is not going to have any turning points. Looking at a quadratic function, we have a degree of 2, which means it can have potentially 2 x-intercepts. And then the turning points where it changes directions, you see it bounces off the origin right here, can have 1. A cubic function, the degree of 3, could potentially have 3 x-intercepts, and it has a maximum number of turning points of 2. A quartic function has the degree of 4, has 4 x-intercepts, same as the degree. Degree minus 1 would leave us with 3 turning points. A quintic function, which is the degree of 5, would have 4 turning points. When we talk about the end behavior, it's a description of the values of the function as x approaches infinity. So we look at it as it approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine its end behavior. So what we do is we set up this chart right here, and we look at the leading coefficients in compared to the degrees. If we have a leading coefficient that is positive and an odd degree, our graph will go down to the left, up to the right every time. If we have a positive leading coefficient and an even degree, our graph will go up to the left and up to the right every time. If our leading coefficient is negative and our end behavior is odd, it will go up to the left, down to the right, and as our leading coefficient is negative, if our degree is even, our graph will go down to the left, down to the right. So this chart you must memorize. Looking at the next examples, it says identify the leading coefficient, the degree, and the end behavior. So when we're looking at example 1, q of x equals negative x to the 4th plus 6x cubed minus x plus 9. We first want to make sure that our polynomial is in standard form, so we start with our largest exponent to the left. So we made sure, and that is in case the fact we have here. When we look at our leading coefficient, we want to state whether it is positive or negative. So our leading coefficient is negative 1. Our degree of our polynomial is this little exponent up here. So we have a degree of 4, and when we talk about our end behavior, if we have a negative leading coefficient and a even exponent, it is going to down to the left, down to the right. So our end behavior, we say, as x approaches negative infinity, our y is also approaching negative infinity. So we're telling where our arrows are pointing. As x approaches positive infinity, q of x, or y, is also approaching negative infinity. Looking at example 2, p of x equals 2x to the 5th power plus 6x to the 4th minus x plus 4. We first notice that it's in descending order, so we're good there. When we look at our leading coefficient, it is a positive 2. When we look at our degree is 5, which is odd. So then we can go back to our end behavior. So if we have an odd degree, so we set up this chart, which you should memorize, even, positive, negative. If we have an odd degree with a positive leading coefficient, it's going to be down to the left, up to the right. So just rewriting this little chart a bunch of times on your paper should help you. So positive and odd is this quadrant right here. So our graph, as x approaches negative infinity, our y is also going to approach negative infinity. As x approaches positive infinity, our y is going to approach positive infinity as well. Example 3 and 4 say identify whether the function graph has an odd or an even degree and a positive or negative leading coefficient. So when we think back to that chart that we should have memorized, and we talk about positive, negative leading coefficient, odd or even degrees, I remember down to the left, up to the right, up, up, down, down, up to the left, down to the right. I can then quickly identify what is happening in my graph. So in example 3, my polynomial is pointing in two different directions. So I know that my degree is odd. And when I look at my leading coefficient, if it is up to the left, down to the right, my leading coefficient is a negative number. Example 4, looking at my end behavior, both are doing the same thing, which tells me my degree is even. My leading coefficient, if both of my arrows are pointing up, is positive. Memorizing this picture is super important. Example number 5 says graph the function based on the characteristics. So we know that our leading coefficient is negative and our degree is even. So if our leading coefficient is negative and our degree is even, we know that both of our end behavior is pointing down. When we look at our zeros, this is telling us all of our x-intercepts. So we have an x-intercept at -6. We have an x-intercept at -2, 2 at -2, and then we have an x-intercept at 3. So after this 6, we know my graph has to go down. After +3, we know our graph has to go down. And then what is happening in between? Well, the fact that we have two zeros at -2 tells us that it has a multiplicity of 2. We also say that -2 is a double root. When we have an even multiplicity, so it happens an even number of times, it bounces. So even number of roots bounce at that point. And if we have an odd number of roots, they cut. So -6 and 3 are going to cut through the axis because that root only happens an odd number of times. So we know when it gets to 2, it bounces, and because these are starting up, our graph has to do something like this. So when we connect our pieces together, we can say that this would kind of look like an M. When we look at example 6, if they want us to graph the function x cubed plus 4x squared plus x minus 6, and they tell us our zeros are at -3, -2, and 1, we can start to interpret some things about this polynomial. I see that -3, -2, and 1 all happen one time, so it's going to cut at -3, cut at -2, and also cut through the x-axis at 1. When we look at the degree, we have an odd degree up here because it's to the third power. When we look at our leading coefficient, it's a +1. So if we have an odd positive behavior, it is going to go down on the left, up on the right. So I kind of draw that in. We can then list as x approaches -infinity, y also approaches -infinity. As x approaches +infinity, y also approaches +infinity. So we have our 3 zeros placed on our graph. We know what's happening at the ends. If our graph has to cut in every one of these locations, it would cut through at -3, cut through at -2, cut at 1. Our polynomial could look something like this.